Hey guys, it's Mr. Ray here. Hope you guys had a good long weekend and did okay on that assignment that was due Sunday night. If you ever have difficulties with the assignment, I've got some students that will send me remind questions, and I'm always happy to help out if you have a question or maybe looking for a hint on something. Um, if you're really, not understanding the lessons, you should be coming for the extra help sessions on Tuesdays and Thursdays. Um, to be honest, with your class, with the calculus class, I think most of you are getting the stuff, but I know there's some of you still struggling, and I'm not hearing from anybody in the calculus class. So um, if you're in that boat where you're struggling, please come for help. Um, I'm more than happy to help out. Okay, so this week, shortened week because of the Victoria Day long weekend, I'm going to be giving lessons. Well, this lesson Tuesday morning and another one Thursday. And what I've decided to do this week is give your class a break. So no assignment this week. So we'll do another couple of lessons next week, Monday and Wednesday, and then the assignment will be a little bit longer than usual. Um, I may release it a bit earlier on. We'll see how it goes. Okay. Um, so we have this one lesson, and you can see by the title of the lesson here, we've really kind of jumped forward into actually the last unit where we do applications of derivatives. Um, this was kind of based on the calculus teachers getting together and deciding what are the most important lessons, and this is a good lesson to talk about before we get into curve sketching, which will be basically the next lesson and probably the next 3, 4, or 5 lessons. And then we'll end off with some application stuff. Okay, so we're skipping all the derivatives of exponential functions, trigonometric functions, ln functions. Um, we're skipping all that, unfortunately, but we will be doing a fair bit of curve sketching and application after this lesson. Okay, so the lesson's called velocity and acceleration, but I know I've kind of told you guys this is like the second derivative lesson. Okay, and you'll soon see why it's affectionately called that. Um, and we can talk about it right here. We know what velocity is. Velocity is the rate of change of the distance or position of an object. Well, acceleration is the rate of change of the velocity of the object. So acceleration is like a rate of change of a rate of change. So in this context, the acceleration is the second derivative of the, I guess I should spell that right, second derivative of the position equation or the distance equation. Okay, so if we put it into context here, we've got s of t, which is your position function based on time. And we've already done this. If we take the derivative of the position equation, we get the velocity equation at time t. So the velocity equation is the derivative of the position equation, or known as ds over dt. Now, if we take that one step farther, we've got s of t, v of t. Now we have a of t, where that's the instantaneous rate of change of velocity with respect to time, which is just called acceleration. So the acceleration function based on time is the first derivative of the velocity function. So a of t equals the derivative of the velocity function. And it's also the second derivative of the position. So you could put these things as all equal to each other. Now, this looks a bit odd. This is Leibniz notation for second derivatives. You can see we've got the two as almost like exponents there and there. I wouldn't worry too much about that, but if you do see it in the book or in questions, that basically means the second derivative of s with respect to t. Okay. Now, if we're looking at velocity, so that's the first derivative of position, and negative velocity means you're moving in a negative direction. So depending on what your what you're measuring. It could be a height, it could be a horizontal distance. Um, the negative direction means the object is going to the left or going down. Okay, and remember velocity from vectors. It's not just speed, it's speed and direction. So you have to mention, is it going up, down, left, right? Okay, and a positive velocity um, means that the object's moving in a positive direction. So it could be going up in the air or to the right. All right, if we go to acceleration, um, a negative acceleration means the velocity is decreasing. So it's almost like taking your foot off the gas pedal. You're decelerating. Your velocity is still positive. You're still going in a positive direction, but your velocity is decreasing. Okay. Same thing with positive acceleration is like when you floor it, like you press the accelerator, um, means your velocity is increasing. Okay. Zero acceleration would be uh, keeping the speed limit 100 kilometers per hour on the 401. Your foot's on the gas, but it's just maintaining that same speed. Okay, so that's acceleration, how it relates to velocity. And then we just talked about zero acceleration. An object is accelerating, speeding up when its velocity and acceleration have the same signs. And an object is decelerating, slowing down when the velocity and acceleration have the opposite signs. Okay, so it could be, well, if you look at this one here, object is decelerating. Let me move this up. Object is decelerating, slowing down. This could be the velocity is positive, but the acceleration is negative. Means it's the object's slowing down. So you can figure that out just by thinking of example of in the car. And the speed of an object is the magnitude of its velocity at time t. So remember, speed, that's the vector. So we don't care about direction. So when you take the magnitude, it's like the square root, really. So you're taking the square root of the speed, not the square root, the absolute value of the speed, knocking off any negative signs. So if the object is falling down to the earth at 100 meters per second, well, the velocity would be negative 100 meters per second, but the speed would be 100 meters per second because speed doesn't care about direction. Okay, so we've got a few different types of examples here. Um, so example 1, an object is moving along a straight line. Its position s of t is given by the graph shown. So this is the time in seconds, I believe. Yeah, I guess it doesn't really say. And this is the position. So this would be moving away from where you are or moving to the right. In this case, because it's talking about left and right along a straight line. When is the object moving to the right and when is it moving to the left and when is it at rest? Okay, so let's look at these separately. So moving to right. Okay, so that means the object is basically moving around, moving away from you, or if you looked at the in terms of velocity v of t, that's where v of t would be positive. So v of t is positive from 0 seconds to 2 seconds. So now between 0 and 2 seconds. And also at 6 seconds, it's also moving away. Okay, it has a positive position. Well, the has a positive speed because the tangent there is positive. So we'd add on t also greater than 6. So between 0 and 2 seconds, from between 0 and 2 seconds and greater than 6 seconds, the object's moving to the right. Moving to the left, okay, so that's where it's the position is coming back towards you. So if you thought about this in terms of derivative, it's a negative derivative moving to the left. Okay, so that would be between 2 seconds and 6 seconds. I'm assuming seconds here. And the last part, when is it stationary? So stationary, you could think about it as changing directions. At what time did it go from moving to the right to moving to the left, or vice versa? And you can see that that's happening here. That's at a local maximum or a local minimum down here. It's changing direction. Okay, but it's also good to think where was the tangent horizontal, right? So the tangent is horizontal there and there. That's another way of thinking of changing direction, or it's at rest at these 2 points. So stationary for t equals 2 and 6 seconds. Okay, so that's how you would interpret the graph. You could take the derivative of s of t, get v of t, and you could look at it from that perspective, but you don't need to take the derivative. You can tell by the graph what's going on. Okay, we have another question here. We have, again, it has to do with displacement, velocity, acceleration. The position of an object moving on a line is given by the equation s of t, so position, st squared minus t cubed for t greater than or equal to 0. S is in meters and t is in seconds. Determine the velocity and acceleration of the object at t equals 2. So first thing I'm going to do is actually come up with those equations. So v of t, I'm going to take the derivative of s of t, so this is pretty quick. That's going to be 12t minus 3t squared. So that'll give me the velocity at a given time. And I can also create the acceleration equation by taking the derivative of the velocity. And so that's going to be 12 minus 6t. So I've got the equations I need depending on what the question is for position, velocity, acceleration. This is asking for velocity acceleration at t equals 2. So this is basically just plugging in 2 for t in the velocity equation. So that would be 12 times 2 minus 3, 2 squared. So that's going to be 24 minus, that's going to be a 12 there. So that's going to be 12, and that's positive. 12 meters per second is the velocity at 2 seconds. And what's the acceleration at 2 seconds? Same idea, we just plug it in to our acceleration equation. So that's going to be 12 minus 6 times 2. 12 minus 12, that's 0. Okay, so 0, and don't forget the units here, meters per second squared. Okay, because it's a second derivative. That means the object is not accelerating or decelerating at that point. It's at rest. Sorry, not at rest. It's the speed is constant at that particular time. All right, at which time is the object at rest? So v of that means the object at rest means the velocity is 0. So we're looking to solve v of t equal to 0. Okay, so we take our v of t equation, 12t minus 3t squared, set it equal to 0. Well, this is a quadratic, so and we've got one side already equal to 0. So let's factor this out. Let's see how we can do this. I'm going to factor out the 3t, and I'm going to be left with 4 minus t equals 0, and put brackets around just to make it look more like a factor. So basically, whenever one of these is equal to 0 is when the object is at rest. So this is going to be t equals 0. This is going to be t equals 4. So therefore, at rest, for t equals 0, or 4 seconds. Okay. Part C, in which direction is the object moving at t equals 5? So we're going to plug this into our velocity. Our velocity tells us is it moving to the right or is it moving to the left based on the sign. Okay, so we're going to find v of 5. That's going to be equal to 12 times 5 minus 3 times 5 squared. That's going to be equal to, that's a 60 minus 25, 75. 60 minus 75 is negative 15. And that would be meters per second. So that means the direction is moving in a negative direction. So all the question is asking, is it moving to the left or the right? And because it's a negative sign in the velocity, object is moving in a negative direction. And we can kind of imply, because it says it's on a straight line, we can almost imply that it's moving to the left, but we have to kind of leave that open because maybe that straight line is up and down, who knows. So we could say left or down. They weren't specific in the question, the direction of that line at t equals 5 seconds. Okay. All right. Part D, when is the object moving in a positive direction? Well, basically what we want to solve is when is v of t greater than 0? Okay, because that is the speed equation, so we've already got that above. So that's 12t minus 3t squared greater than 0. Okay, now this is an inequality. It's a little bit tricky. You have to remember from grade, I guess it'd be advanced functions, a little bit from grade 11 maybe. This is still a quadratic, so we can factor this. So again, just like I did in part B, factor out the 3t, and we have 4 minus t left over. Okay, now this is where we'd use our interval, our number. I'm not sure how you guys were taught this, but I think by far the best way to do it is with using intervals. So we've already decided, we already know at 0 seconds and 4 seconds the velocity is 0. So we can put those numbers there and it keeps going. So these are, we're going to learn more about these in the next unit. These are like critical points. Something interesting is happening there with regards to the graph of this equation. So we know that in terms of the velocity at those 2.0 and 4 seconds, the velocity is 0. Okay, so what we do, we pick, we have basically two intervals here between 0 and 4 seconds, what's going on, and greater than 4 seconds, what's going on. We don't need to look at less than 0 because that's negative time, so we don't have to worry about that. It's already told us t is greater than 0, I believe, in the opening statement. So here we can just put some test values. Okay, so I'm going to pick 1 second for that interval and 5 seconds for here. So if you plug in t equals 1 here, you get 3, and all we really care about is it positive or negative. So I plug a 1 in here, that's positive, that's also positive. So I have a positive times a positive, so overall that interval is going to be positive for the velocity. And if I do plug the 5 seconds in, I get a positive value for the first factor and a negative value for the second. So overall, negative times positive, that's going to be negative. So the graph will actually look something like this. It'll be above there. So the question is, when is the object moving in a positive direction? It'll be that interval there where the speed is positive. So therefore, object is moving in a positive direction when t is between 0 and 4 seconds. You have to be careful. You can't put the equal signs there because at 0 seconds and 4 seconds, it's not moving at all. It's stationary at those 2 points. Okay, which is what we answered in B. So you have to put the less than or greater than signs, not equal, less than or equal to. Okay. Now in the completed lesson notes, I realized I did this slightly different. I didn't do anything wrong, but I actually factored out something. I divided by a negative and I flipped this direction around. It was a little bit more confusing doing it that way, because then you're looking for when is the graph below, which seems to contradict the velocity being positive. So I prefer the way I've done it here compared to the way I did it in the completed lesson. But if you have a look at it, maybe you'll understand what I did. I just divided by negative, which means I had to turn around the inequality sign. Okay. When does the object return to its initial position? Well, we don't really know its initial position. So we can't assume it's at 0. We have to find out. So s at 0 seconds, the position at 0 seconds, we take our original equation. So that's 6 times 0 squared minus 0 cubed. And sure enough, that is 0. But you still have to check it. It doesn't have to be starting at 0. So that's at 0 meters. So when is the object at 0 meters again is basically how we can reinterpret this question. So we take that answer of 0 and we set our original position equation, 6t squared minus t cubed. I want to find out what value of t will make this statement true. So again, we're going to factor. So in this case, I'm going to factor t squared. Factor t squared out, so I get t squared times 6 minus t. And you can see from here, for that to be 0, t would be 0. And for this to be 0, t would be 6. So the object is at 0 meters, at 0 seconds, and at 6 seconds. Well, 0 seconds, we already knew that. Okay, we just figured that out. But when does it return back to 0? It returns back at 6 seconds. So therefore, object returns to its initial position at 6 seconds. Okay, so you can see all the things we're able to do just from being given that position equation. We're able to find out all sorts of things. Which direction is the object moving? There wasn't anything asked here about acceleration, except for the plugging in at the beginning. But we could have been asked when is the object accelerating, and done something similar to what we did here. So if we go to the next question. Okay, this is a little bit of a tricky question. It's pretty open-ended here because it just says discuss. It doesn't really talk about find this value at this time, or at what time did this happen. It's kind of open-ended, so not a big fan of this question, but just leaving it open, you could imagine how much information you can actually pull out. Because it says discuss the motion of an object moving along a horizontal line if its position is given by s of t equals t squared minus 10t, and we're only looking at the interval of time from 0 to 12 seconds. S is measured in meters and t is in seconds. include the initial velocity, so at least it's giving us a little bit of a guideline. Include the initial velocity, final velocity, and then acceleration in your discussion. Okay, so again, the first thing let's do is we've got the position equation, S of t. Let's get the velocity equation by taking the derivative, so that's 2t minus 10. And the acceleration, which is the derivative of the velocity equation, well, that happens to be just 2. So right away, that's kind of interesting. The acceleration is constant. Okay, its acceleration is never changing at any time. So it's getting faster and faster as we go. So it want to know about initial velocity, final velocity. So the anything initial, well, that would be at 0 seconds, and the final anything final velocity, position, acceleration, that would be at 12 seconds. So let's look at t equals 0. Let's get the position. So s of 0, if I go back to the top equation here, 0 minus 0. So the initial position is at 0 meters. The initial velocity, if I plug in 0 here, that's going to be negative 10 meters per second. So that tells you, sorry, to put my negative sign there, that tells you the object is moving to the left right from the beginning. Not sure how long for. And then the acceleration at 0, well, we've already determined that's always going to be 2. Doesn't depend on the time, meters per second squared. So put all that in a little information box. So at the initial time, starting time, that's the position, the speed, and the acceleration. Okay. Now, if we go right beside here, if we do at t equals 12, this will be the final, like at the end of the study, at 12 seconds. So the position at s of 12, if I plug that in, I'm going to get 144 minus 120, so that's 24 meters. And that means it's to the right, okay? So the final position is to the right, but remember here, the initial velocity was moving to the left, so something happened where it changed direction and ended back 24 meters to the right, okay? The velocity at the end, at the 12 seconds, we get 24 minus 10, so that's 14 meters per second. And the acceleration, of course, that's always going to be 2 meters per second squared. So there we've got basically our initial information, our final information. So we've kind of determined that somehow, at some point, the object changed direction because it was moving to the left to start and it ended up all the way over 24 meters to the right. So the way we can find that is find out when the velocity is equal to 0, and that tells us basically when it's changing direction. Okay, so we just plug this into our equation. 0 is equal to 2t minus 10. And if we solve that, 2t equals 10, so that's t equals 5 seconds. So that says the object is changing direction at 5 seconds. We could also say, well, where's the velocity positive? So this would be, I'll turn it around this time. Velocity is greater than 0. So this would be 2t greater than 10. T is greater than 5 seconds. Okay, so these two things together, we could do less than 0, but basically that's going to be between 0 and 5 seconds. So at 5 seconds, that's when the object changes directions. Okay. Yeah, I might as well do the velocity less than 0, just to be complete. 2t minus 10 less than 0. So that means 2t is less than 10. Now, you'd think there'd be t is less than 5, but we had that the time it can't be lower than 0. So 0 between 0 and 5 seconds is when the velocity is decreasing, is negative, sorry. Now, I kind of cut my room back here, but I'd like to kind of show you with this number line what's kind of going on. So we basically know that this is the position S of t, so that's at 0 meters, and we know it went all the way out to 24, so it ended there, started there. Now, one thing we didn't do, so we know for the first 5 seconds it was going left. So it'd be nice to know, well, how far did it end up going before it turned around? So we could plug that in. We could say, well, what's the, not velocity, what's the position, S of 5. S of 5 is equal to, that's going to be 25 minus 50, which is negative 25. Okay, so I'll just put my negative 25 out there. The scale is a little bit off, you can see that. So basically, the object, so this is the path of the object. So at 0 seconds, it started here at 0 meters. It went all the way up to here, and then turned around and this happened at 5 seconds. And then it traveled all the way out to 24 meters at 12 seconds. So you can almost see what's happened with the position based on the information we pulled out from the 3 equations. So you can see it's very powerful with first and second derivatives of a position. You can find out exactly what's going on when it's changing direction, speeding up, slowing down, left, right, up, down, all sorts of information. Okay, now, like I said, this is a pretty open-ended question. All they really asked for was, this information, but they wanted you to discuss it. So I guess I didn't really do a lot of discussing yet. So discuss means use words, which I always tell you guys. So the object moves left for t between 0 and 5 seconds. The initial velocity is negative 10 meters per second. Final velocity is 14 meters per second. And that's what we got from these 2 boxes where we started. Okay, so you could really, like I said, you can really get a lot of information just from that one equation using derivatives. So you can see how this is useful for applications. Now, here's a question. Let me get this straight for you. Here's a question that you could have easily been given in grade 10. We're going to use derivatives to answer this question. Okay, a baseball is hit vertically upward. The position function S of t in meters of the ball above the ground, so this is like a height function, is S of t equals negative 5t squared plus 30t plus 1, quadratic, opening down. You see these all the time in grade 10 for quadratics, grade 11 as well. Determine the maximum height reached by the ball. Well, in grade 10 we would have said, well, that's a vertex, so find the vertex. So we're not going to do it that way. We know that the maximum height is reached when the speed is 0. Okay, so we want to solve for when v of t equals 0. Well, what's v of t? Well, v of t is the derivative of s of t, so that's going to be negative 10t plus 30. Okay, so when I set that 0 equals negative 10t plus 30. That means 10t equals 30, t equals 3 seconds. So the speed of the ball is 0 meters per second only once, and that occurs at 3 seconds. Okay. So how do we get the maximum height? Well, we just plug this back into our position equation. So then s of 3 is equal to negative 5, 3 squared, plus 30 times 3, plus 1. And that is, so I got a 9, negative 45 plus 90. So that's 45. To get 45 plus 1 is 46 meters. So the maximum height of the ball is 46 meters. Okay? If only you knew that in grade 10, could have saved you a lot of aggravation about quadratics, right? But it's interesting to see a totally different approach to answer the same question. So we're not even discussing vertex, we just happen to know that the maximum height happens when the speed is 0 and solve for that. Okay, second question, determine the velocity of the ball. Now this you wouldn't have been asked in grade 10 because this is just position. Determine the velocity of the ball when it's caught 1 meter above the ground. So that means s of t is equal to 1. The position is 1 meter. So we set our original equation equal to 1. Negative 5t squared plus 30t plus 1 is equal to 1. And these ones will cancel. And that worked out nicely because now we can factor out negative 5t. And I get t minus 6 equals 0. So when is this true? It's true for t equals 0 and t equals 6. And t equals 0, well, that was when the person threw the ball, right? So they threw it 1 meter off the ground, or maybe it was hit off a tee or something like that. So that happened when the ball was hit or thrown at the beginning. And 6 seconds is when it was actually caught. Okay, so we can, through a little bit of reasoning, you can figure out that's when the ball was caught. Okay, but that's not the question. The question is what's the velocity when it was caught? So now we plug that time into the velocity equation. So that's going to be negative 10 times 6 plus 30. So that's negative 60 plus 30. That's equal to negative 30. Okay, so what does that mean? Well, this is a speed. No, sorry, it's a velocity. Velocity with a negative value, so that means the ball was coming down. So velocity of ball when caught was negative 30 meters per second. And if you wanted to, you could say that it was going down at 30 meters per second. Sorry, squeeze that in there. Okay, so I think this is a good place to put this lesson in. I know it's really from applications, and we looked at the application of, quadratic applications with the velocity and time. And we're going to come back to this at the very end. Okay, so probably in a couple of weeks, we'll come back to this, and we'll look at other ways we can optimize, look at application, ways of optimizing things, finding out stuff that you maybe had another way of doing it in grade 10 or 11, and now we're looking from a calculus perspective. Okay, so there are some questions here. Now, I didn't look at this before. This would be the questions I would assign for a full course. So if you see any questions involving exponential functions or trig functions, anything other than polynomial functions, you can just skip those. Okay, so that'll probably reduce the questions by a bit. Okay, All right, guys. So another lesson on Thursday to come out, and just a reminder: uh, no assignment this week. So that's good news. Two more lessons next week, and then an assignment. Okay. Thanks, guys. Have a good day.